Okay. So, we're going to learn about Riemann sums. Okay. So, Riemann was exploring this idea of area under the curve, and obviously toilet paper squares that are not working for him. He needs a systematic approach for this. So, I did not let you split up your pieces of toilet paper, like cut them in half, because I'm working towards this idea of Riemann sums, and Riemann sums are done completely with rectangles, right? So by not letting you cut your toilet paper, you pretty much had to be working with rectangles, right? Now, each one was a little square, but you could sort of think of this as being a rectangle, and this one right here as being a rectangle, and then the next one as a rectangle, right? For a Riemann sum approximation, there are two things that we must know before we start our approximation. The problem is going to tell you how many rectangles or subintervals that you are going to use, and whether or not you are going to be using a left, right, or a midpoint sum. And then we will also learn a trapezoidal rule. Midpoint we're not going to do today. We're just going to do left or right. We're going to start off with two very simple examples. Okay? If you are using a left Riemann sum with two subintervals, so these are not, actually, I got us with one subinterval right here. One subinterval, that means one rectangle, right? Then you get pretty bad results for this, right? Like a lot of these Riemann sums, whenever we do them, our results are going to be kind of terrible. But we're using a systematic approach for it. What's going to happen is the systematic approach could be improved infinitely. As a limit approaches infinity, we get the exact answer for that. If I only have one subinterval, that means one rectangle, right? And if I'm using a left Riemann sum, that means that the left vertex of the rectangle is on the function. Okay, so if I look at this graph right here, and I'm going to use a left Riemann sum, that means I need to draw a rectangle, in this case just one rectangle, and the left-hand corner of that rectangle has to be on the graph. So what that would look like here is this left corner right here, I would have this rectangle. Okay, that would be a left Riemann sum for this. Let's see, does he introduce that notation later? No, I'm going to start using it right. No, it does later. So, even though I'll start using it right now. So, whenever we are looking at this area under the curve, it's going to be the idea of integration. So, this is going to be where we bring in the symbol that you've probably seen here on some stuff I've given you that you can't do yet, right? This symbol is the integral symbol, and sometimes it will be alone, like this, and other times, like now, you are going to put a number at the bottom, in this case it'll be 0, and a number at the top. And that is the domain that you're looking at, right? So the integral from 0 to 2 of, they're calling this function right here, VQ of t. And then whatever variable goes, is your independent variable, whatever's inside the parentheses there, we will put a dt over here on the end. That's telling you, what you're integrating with respect to. We'll get into that, details of that a little bit later. Just know that this letter and this letter always match, and that one right there is always a D. So whenever you see that notation right there, it means the area under the curve of V sub Q of T from 0 to 2. Right? That's what we're talking about. So to estimate this, when we estimate, we use the squiggly equal sign here. And in this particular case, we just have one rectangle, and it has a height of 1 and a width of 2, so my estimate is 2. Is this a very good guess? No, it's not close, right? But it is a guess. Now, the problem didn't ask us to do this, but if well, let's see. Does it have me do it later? Oh, it has me. Well, it doesn't have me do it with one rectangle. If I'm doing a right Riemann sum, then the right endpoint is going to be on the graph. So, like, if it had asked me to do a right endpoint Riemann sum, the right endpoint would be on the graph, and it would look like this, and I'd get 6. Also, not a very good estimate, right? But I would know my real answer needs to be between 2 and 6, right? So I would have some parameters there. Now, normally we do not use one subinterval. Normally, they ask for more. Everything on the exam is usually at least 3 subintervals. 4 is a really common one for them to ask you for on the exam here. So if I want to do the same thing here, did it give me the equation for this? It did not. But I am pretty sure. I'm going to add this in. This is the first time I've used Mr. Passwater's notes here. I might need to adjust it a little bit more. I am pretty sure the equation of this is V sub Q of T equals 1/2 x squared plus 1. I'm pretty sure. Because it looks like a quadratic that's been moved up 1 and squished to me. So I'm pretty sure that's our equation. I'm going to say it is so that we can, I want us to find this exactly here. So if I want to do a left Riemann sum with 2 equal subintervals, right? Well, we generally want to think of our rectangles as being like vertical rectangles, right? So that means my interval is from 0 to 2. So if I'm splitting that into equal subintervals, then that means I'm going to have 2 rectangles. Each one of them are going to have a width of 1, right? And so I want the left corner of my rectangle to be on the graph. So the first rectangle would look like this, right here. And then the second rectangle, I want the left corner right there to be on the graph. Now, the first piece is pretty easy to do. This is an estimate, so I'm going to say the integral from 0 to 2 of V sub Q of T dt. That means the area under this curve from 0 to 2 is approximately. I know this first rectangle is just 1 times 1, right? Or if you just want to put 1, that's fine. But then the second rectangle, the width is 1. How could I find the height? Because it's not a whole number. I could estimate, because I am estimating anyway, but there's a way I can know the exact height of that rectangle. What can I do? The left endpoint of this, the left endpoint right here is on that function, right? So if I want to know how tall this rectangle is, that's the y-coordinate of that point, correct? And so the x-coordinate here is 1. I need to find that y-coordinate, and that'll give me that height. And so since I gave you the equation, which I guess Mr. Passwater was just wanting you to estimate, but I want the exact number. I could do V sub Q of 1, which would be 1/2 times 1 squared plus 1, and that's just going to give me 1.5, which is probably what we would have guessed if we were estimating anyway, but I like to get the exact number. And so this estimate is going to be 1 plus 1.5, so we will get 2.5 for this estimate. Now, I am not going to make us do this here because it starts to get very tedious, something that takes forever. But how could we make this a better estimate? If we still use rectangles and we still put the left endpoint on the graph, what's something we could do that would give us a better estimate? Because right now it's still not very good. Keep that idea in your mind. We're going to keep going. Okay? Right Riemann sum. Okay? The right Riemann sum with two subintervals, right? We're still using the same graph. So this is still V sub Q of T is 1/2 T squared plus 1. And so the right Riemann sum means that the right vertex of the rectangle is on the curve. Now, I like that you said, does that mean it's going to be above the graph? For this one, it does. But, is that always the case? No. Yes?
So, when we're doing these, like, how do you know the equation?
It'll be given to you it'll be given to you here, since I'm using, I think Mr. Passwater was just got kids to just guess on this one, but if I want the exact value, it'll be given to you for that. So I've added it in because I want to do it that way, but we'll find they don't actually give it to you with the equation too often. We're going to see it from tables or graphs more often where they give you like nicer points to deal with. But if they want you to give the exact from the equation, they'll give the equation to you. So we got integral from 0 to V sub Q of T dt. That means the area under the curve here from 0 to 2 is approximately, now for these rectangles, same thing, two subintervals from 0 to 2. So each one of these rectangles is going to have a width of 1. But this time, you want the right end point of the rectangle to be on the graph, which means that your graph will look like this. Now, we already know how tall this first rectangle is, don't we? How tall is that first rectangle? I know it has a width of 1. How tall? It's 1.5 because this is that same point that we just found a little bit ago, right? Here, but it ends up being the first rectangle instead of the second for this one. And then the next one's easy to count. It's just going to be 1 times 3. So we would have 1.5 plus 3, and we'll get 4.5 for our estimate. Okay. Now, for this one, we definitely know this is an overestimate, right? All of our rectangles are going above our graph. For the example 2, that was definitely an underestimate. So we at least now sort of have it narrowed down. I know that my answer needs to be between 2.5 and 4.5, right? It's a little bit smaller interval. When we are looking at this, look at this picture. This is the same graph. We're not going to actually calculate it, but these are all left Riemann sums because you've got the left endpoint of your rectangles are on the graph there. And you can see for this function, you're getting an underestimate for all of these. But which one looks the best? Which one looks like it'd be the closest? The last one, the one that has the most rectangles, right? Because now on this one, it's harder to calculate because what's the width of each little rectangle there? 0.25, right? Because you got like 4 rectangles per unit on this graph. So like you'd have to do 0.25 times 1 for that first rectangle, and then 0.25 times, and then you got to use your equation to find the height of that second rectangle, and 0.25 times the third rectangle. And so it's going to take a while to figure that out. And that's something we're not going to actually do that often for larger values, but this is a better estimate here where I have more rectangles. If I wanted to get an even better estimate, I could use 20 rectangles, or 100 rectangles, or 1,000,000 rectangles, right? I'd be here for the rest of the time if I used 1,000,000 rectangles trying to figure it out. But what would give me a perfect fit? How many rectangles would I need? Infinite rectangles, right? So the exact area, we would need infinitely many rectangles. Now, this is the idea that we're going to kind of skip the mechanics of. We're going to learn how to estimate, and then I'm going to kind of skip over the part where we do the limit definition and like figure out how to calculate it with limits because we're out of time and we need to move on. But that's the reason that they have us doing these calculations here, is because we are going to do these estimates and they're going to be like okay, and we can make them better with more rectangles, and then we could take this and systematically do the limit as x approaches infinity of those rectangles. Now, I'm skipping a big piece there, so it kind of makes it seem like a bigger jump than it would really be. But and also, like, this symbol right here that you see is a sigma. It means to add up, right? So if we think about the rectangles here, all of the rectangles in all these situations have the same width, right? Because we're using equal subintervals. So I could sort of like factor that out, and then I multiply it by all of the y values. So if I add all of that together, this is saying add the height, which is your f of x, your y coordinate, times the delta x, which is your width of your rectangle. If you add all those together, then you get your estimate for this. So we're going to totally skip everything with sigma notation because we just don't have the time to do it like we need to. But when you run into this, like if you see this somewhere, it's telling you like you're adding up those things. We are not going to actually use that notation to do anything with it there. Instead, we are just going to write the integral from a to b of f of x dx, and we're going to use the squiggly equal signs to show we're doing approximations here. So, the key concept here is that this is an accumulator. We're adding up the signed areas of this rectangle. Now, so far, I have only done areas above the curve, so everything is positive. Later, we'll talk about how if we've got places that dip below the x-axis, that area is going to be negative. But that's not going to be necessarily something we have to do today. I do want us to think about the notation that we're going to use here a little bit. So if I have here, write an expression involving a definite integral that represents the shaded area in the figure below, we're talking about, when we're writing this equation, we are finding the area under the curve. What's the name of this curve? H of x. And since there is an x on the inside of that parentheses, I'm going to put a dx here with that. And then what are our limits that we're looking at here? 2 up here, 2x. Okay, so that's one thing you're going to be asked to do on your homework tonight is just look at a picture and translate it to that notation. So it should be quick. You're just thinking about what you're doing there. If I want to write a definite integral for this one, then I would just have the integral of f of x. I'll put a dx because x is my independent variable. What's my lowest limit? What's the furthest left we go here? -5. What's the furthest right? 4. Okay, so that should be quick. Let's do one. Okay, we're going to do this one from a table. It's going to take to the last second here, and then hopefully that'll at least be enough for us to calculate. We probably won't be able to interpret very much on the homework tonight. So if I want to make rectangles for this, then I need to think about whether I'm using a left Riemann sum or a right Riemann sum. And I want to think about the width of each rectangle and the height. Okay? Now, is the width of each rectangle the same on this table? No. Like from 0 to 2, right? That has a width of 2. Since this is a left Riemann sum, like if you're thinking about graphing this, you've got the point 0, 11 right here, right? And then you got the point 2, 30. You're doing a left Riemann sum. You want to pick the left endpoint, right? So we would do 2 times 11. Then we need to think about the next section, the next rectangle. Well, that goes from 2 to 4. Still a width of 2, because from 2 to 4, that's 2. So my width is 2. What would I use for my height? Think about this next rectangle. You're going to do 30. 30. So whenever you do this, it ends up being like this goes here, this is going to go here, right? For a left Riemann sum. If it was right, we would be choosing 30, 54, 20. Yeah, we'd be choosing the next ones. So this only has a width of 1. And then the left height is going to be 54. From 5 to 6, that's just a width of 1. What's the height there? 26. From 6 to 9, that's a width of 3. Oh, I've messed this up. I'm using 6 subintervals. Pretend that said 6. And you'll have 21. And then this last one would be 3 times 44. Okay. And then you would figure that out. That's going to be your estimate for that particular one. So, we're going to be able to do some, but not all of this worksheet. Alright, you should definitely be able to do the notation stuff on number 4. Just try the front page, okay? On number 3, you don't have to really, tell me about the meaning of it because we didn't really get into that too much today. But just try the front page. It might be helpful to graph these points right here, to like get yourself a little, graph over to the side, and that might help you see what the rectangles look like. So try the front page. You don't have to do the back. We will finish up these notes and then start into the midpoint and trapezoidal rule tomorrow.